All right, welcome back, folks. In this video, we'll be looking at the first method in solving differential equations. So we'll be looking at how to tackle solving first order differential equations in the first few videos, okay? And I want to start off how this method was formulated by looking at motion of falling bodies. This goes back to the time of Galileo when he formulated the equations for projectile motion. So let's get started. So as you recall, by Newton's second law of motion, right, the force applied to an object is equal to the object's mass times the acceleration, right? So A of t is the acceleration, right? And then m is just an object's mass, right? It's the mass of the object. So m is a constant, and then A of t is just the acceleration with respect to time, right? And as you know, the acceleration is the derivative of the velocity. So we can express Newton's second law of motion as the F equals m times dv dt, right? F denotes the force of the object, okay? And then dv dt is just the change in velocity with respect to time. So acceleration, right? So this equation only considers the fact that there are no external forces besides the gravitational force that is applied to an object that's falling towards the ground, right? So if you have an object falling towards the ground with no external forces besides gravity, this equation can be applied. But in some instances, we're going to have to take into account the object's drag and, or I should say drag coefficient and the air resistance, right? So this differential equation will be changed a little bit, right? So this differential equation here will be changed, all right? So in terms of the vertical force applied to an object, we're going to have to think just a little bit clearly here, right? So it's going to be convenient to label the velocity as a positive quantity, right? When the object is moving downwards. So this is important, okay? So in terms of a projectile motion, so near the surface of the Earth, the acceleration is just the gravitational acceleration. So 9.8 meters per second squared, right? The object's gravitational acceleration, okay? And so it will be labeled as m times g, okay? So this will correspond to the vertical force acting on the object in the negative direction, so n times g. So what that means is we'll label this quantity, air resistance, as minus b times v, right? So minus b times v. So b is a positive constant, and this will depend on, well, the density of the air and the shape of the object. So this will look at the drag coefficient, right? And then the air density, looking at the air resistance, right? And so with this motion, right, the gravitational acceleration is pulling down the object, while at the same time, there is friction that is acting against the object, namely air resistance, right? So it's dragging upwards. So now the differential equation will become an equation that looks like this, right? So, so this would be the following differential equation, all right? So let me, I got to zoom out here. Crap. I got to zoom out here and erase it. So, yeah, so let me erase this here. Can I erase it, please? There we go. Oh God, what did I do? don't freak out on me again. Um, so this is Newton's second law of motion right here. So the right-hand side is just the sum of all the forces. Sum of all the forces acting on the vertical and horizontal. So there's no horizontal forces, right? The ball is, I'm sorry, the object is just going the object is moving vertically, right? So mg minus bv is just the sum of the vertical forces acting on the object. And then the left-hand side, this is just mass times the acceleration. So this is just your basic Newton's second law of motion that's occurring here, right? So let me erase all of this here. Okay, so now the primary goal in here in this equation is to solve for a general solution, right? Okay, so we're going to look for the general solution of this equation. And the technique we're going to use is what's called separation of variables. And I'm going to show you just the technique on how to derive the general solution for this equation. Okay, so algebraically, so we have this equation right here. So v is a function of time. And m is just a coefficient. So if I have m times dv dt equals to mg minus b times v. Okay, so separation of variables. The primary goal is to gather all of the variables of one type to one side and the other variable to the other side of the equation. All right. So you've seen in calculus before that we can't really separate this quantity dv dt, right? But it turns out you can separate it. And I'll show you what I mean by this. So first of all, if I divide both sides by m in this equation, I'll have dv dt equals to m times g minus b times v over m. All right. So now what I want to do next is, well, we can multiply both sides by dt, right? By dt. And so what happens now is we'll have one side that has dv in it. And the other side, well, this will turn out to be m times g minus b times v over m times dt, right? Times dt. Okay? So now our goal here is to gather all of the variables of one type, okay, and moving it to the either the left or the right hand side of the equation, right? So we have let me do another color. So we have this quantity, right? mg minus b times v over m, right, as a function of v. So we want to gather that quantity itself um, uh, onto the left-hand side. That's where the V is, right? And so if I multiply both sides by that quantity, right? So M over mg minus bv, right? And so this would equal to, so m over mg minus b times v dv equals to dt, right? Or maybe I can just leave so m is a constant, right? So it doesn't matter, m goes on the left or the right-hand side. So it's probably best if I leave out this constant m on the left-hand side. So 1 over m dt, and this equals to 1 here. Okay. So, right. Okay. So now our next step is to integrate both sides. So we're going to integrate both sides of this equation, right? So we're going to integrate both sides. And I'm going to erase this to get some room. I'm going to need it. Oops. Darn it. Okay. Okay. So if we integrate both sides, so what we have is I'll have so the right-hand side. This is t over m plus c1. I'll label this as c1. So c1 is a constant. It's just arbitrary constant here, right? Constant. All right. And so, and there's a antiderivative for an integral that looks like this, I believe. But yeah, it's better off if I'll just use sub for the left-hand side. So if I use u is equal to the quantity on the denominator on the left-hand side, du is or I should say dv, sorry. So that's 0 and minus b times dv. And the left-hand side, in terms of u, will have so minus 1 over b times oh, Jesus Christ, 1 over u du. All right. So this is minus 1 over b times the natural log of the absolute value of u. That will equal to n times g minus b times v. And then the right-hand side will just still be t over n plus c1. Okay. And so we'll have, so what this means is the left-hand side becomes ln of mg minus bv. And this equals to Jesus. This equals to minus bt over m minus c1. And then we want to solve for v. So if we take the Euler's constant to both sides, so this right-hand side will be mg minus bv. It should be brighter. Mg minus bv equals to, so that will be another constant, C2. So e to the minus c1, that's just another constant. So it'll be c2 times e to the minus bt divided by m. Okay. And then from here, we're going to solve for v, right? Solve for v here. Okay. So we'll have minus bv equals to minus mg plus c2 e to the minus bt over m. And so if I solve for v, so this is a function in t, so this would equal to so okay, so we'll have mg over b minus c2 e to the minus bt over m. Okay, so this is the general solution. Okay, and then usually you'll have an initial velocity. So this right here, v naught. So v naught is the initial velocity of the object. So it's the initial vertical velocity. Okay. So yeah, this right here is the general solution, and if you have v of 0 equals to v naught, so yeah, so yeah, so typically you'll have initial velocity, and so you'll have yeah, this general solution for this differential equation. Okay. And so if we solve for a particular solution, so basically it will look like this, right? And that's what we had right here, m times g over b. Uh, so it'll be plus if we figure out what v naught is, right? So, or I should say what C2 is, right? So it will be v of 0 equals to, so this will be yeah, so this quantity would be 0, and yeah, all right. So minus C2 equals v naught. Yeah, so it'll be v naught minus mg over b. So okay, yeah. All right, so okay, so they had this plus because regardless of C2 is a constant, so they just label it as a plus. But regardless, right, you'll get C2 as V naught minus mg over b, right? So yeah, nevertheless, you'll get the particular solution looking like this. Okay, so V naught is the initial velocity. B is just a constant that includes the drag coefficient of an object and the air density, right? What is needed for air resistance. Okay. And then terminal velocity. is where the velocity is not changing, right, as the object is falling. So you have a constant velocity. So as time uh, as time moves forward, right, you'll have the vertical velocity approaching to this quantity, mg over b, in this particular solution, right? So that's one way to calculate terminal velocity. But really, the other way is, well, it's where the velocity is zero, right? So you have, so your velocity is not changing, right? And so you'll have the velocity equal to mg over b, right? That's another way to compute terminal velocity. All right. So let's do an overview of what separation of variables is. Okay, so this algorithm. All right, or procedure. If you have the right-hand side of a differential equation, dy dx equals to a function of x and y. If this function can be expressed as a product of a function in x and a function of y, right, then you can classify that differential equation as separable. So in other words, if you can express dy dx as a function of x times a function in y, right, then you can classify that differential equation as separable, right? So the steps here is just like I labeled out before, right? So in this case, if you have an equation that is written out as a product of two functions, right? G of x times P of y, let's say. So you want to multiply both sides by dx, right? And then you also want to multiply by h of y, or you can multiply both sides by 1 over P of y, right, to obtain this relationship, right? You have a function of y times dy, and it equals to a function of x times dx, right? Then the next step is to integrate both sides, right? We have to integrate with respect to y on the left-hand side, and then integrate with respect to x on the right-hand side of the equation, okay? So you'll have this following relationship here. C is just an arbitrary constant, right? You'll get both constants when we integrate y and x, but they label capital C as the universal constant for the antiderivatives for x and then y, okay? So yeah, they merged the two constants into one universal one, capital C, right? So the last equation here just gives you the general solution, right? But it's written out implicitly, okay? Oftentimes you can solve for y explicitly, okay? But it's also valid to express it as an implicit equation, right? So let's go over some examples on classifying if equations are separable or not. So, for example, if you have these two equations, right? ds dt equals t times the natural log of s of 2t plus at squared, plus, and in part b, right, we have dy dx, and that equals to 2x divided by y squared times x plus 3. All right. I want you to pause the video and try to figure out if these two equations are separable or not. If it is separable, try to figure out a general solution. Okay. All right. So I assume you worked on these examples. Part A, we have to see if this differential equation, ds dt, is equal to a product of a function in t and a function of s, right? Well, this is not a separable equation, because of this plus sign here. That will cause problems. And also another fact here is that we have a factor of t here, and we have also another factor of t squared. So that also causes problems too. So in this case, this equation here, this is not separable. Not separable. Okay? Not separable. Okay? But this one, if you notice, dy dx is equal to, well, if I write out the function like this, 1 over y squared times 2x over x plus 3, then it is separable. It is separable. So let's actually figure out the general solution for this equation, right? So we have dy dx is equal to 2x over y squared over x plus 3, right? So first step, we want to gather all of the y variables on the left-hand side, okay? And we want to gather all of the x variables to the right-hand side of the equation, right? So first step, let's multiply both sides by dx, right? dx. All right, so we'll have dy equals to 2x over y squared times x plus 3 dx, right? And then what we can do next is multiply both sides by y squared, right? Y squared. So the y squareds will cancel. And then we'll have, if I just write it over on this side, so we'll have y squared times, let me give out some more space. So if I have y squared dy equals to 2x over x plus 3 dx, right? All right. So we have all of the y variables and the x terms on their respective sides, right? And so the next step is to integrate both sides, right? Okay. So on the left-hand side, we will have 1/3 y cubed, right? Just by the power rule for integration. This right-hand side, this will use a u sub. So if I use u equal to x plus 3, right? du is equal to just dx, right? And so what that means is if u is equal to x plus 3, then x is equal to u minus 3. And so on the right-hand side, in terms of u's, we'll have the integral of 2 times u minus 3 over u times du, right? And so if I erase this here, give out some more room, we'll have so 1/3 y cubed equals to 2 times the integral of 1 minus 3 over u du, right? And so we will have 1/3 y cubed is equal to 2 times u minus 3 times the natural log of the absolute value of u plus c1, right? And so we'll have since u is x plus 3, excuse me, so we'll have 2 times x plus 3 minus 3 times ln of x plus 3. And then we'll have another constant, C2, right? All right. 2 times a constant is just another constant, right? And then the left-hand side is equal to 1/3 y cubed. And to solve for y cubed, we'll have so to solve for y cubed, we'll have so we'll have y cubed is equal to 6 times x plus 3 minus 3 times the natural log of x plus 3 plus C3 plus another constant. And so the particular solution, if we cube root both sides, so this would equal to the cube root of 6 times x plus 3 minus 3 times the natural log of the absolute value of x plus 3 plus C3. C3 is just an arbitrary constant, right? So that right there is the general solution, okay? So hopefully that made sense. And so that's about it for this technique. We will go over different types of first order differential equations, like linear differential equations, exact. And yeah, those are it off the top of my head. But here's some problems for you to check for comprehension. It's in the textbook. And most of these deal with separation of variables. This one is an application problem for a stirred tank, right? Pretty fun, right? But otherwise, you have questions or comments, please send them out to me, right? Or leave it in the comment section. So other than that, I hope you enjoyed this lesson. I will see you all in the next one. Take care.